Hello and welcome to the session. In this session, we are going to discuss how to solve system of equations using Gaussian elimination method. Before we start with Gaussian elimination method, let us discuss row echelon form of a matrix and augmented matrix. A matrix is said to be in row echelon form if the first non-zero entry in each row is 1. The rows are arranged in such a way that the first non-zero entry in each row is to the right of the first non-zero entry in the previous row. That is, all entries below the leading entry of the row are 0 in that column. The entries before the first non-zero entry in each row are 0. The rows whose all entries are 0 appear at the bottom of the matrix. Let us see the following matrices. First, the matrix containing elements 1, 2, 3 in the first row, 0, 1, 2 in the second row and 0, 0, 1 in the third row. The second matrix is the matrix containing elements 1, minus 2, 0, 0, 0, 0. And the third matrix is 1, 0, 2, 0 in the first row, 0, 0, 1, 4 in the second row, 0, 0, 1, 0 in the third row. The first matrix is in echelon form because here all the conditions are satisfied. The leading entry in each row is 1. We see in row 2, the leading entry is 1 and it is to the right of the leading entry of row 1. Also, all entries before this one in row 2 are 0. Similarly, in row 3, the leading entry is to the right of the leading entry of row 2 and all entries before 1 in the third row are 0. The second matrix is also in row echelon form See here, the row whose all entries are 0 appear at the bottom of the matrix. In the third matrix, the first two rows satisfy the conditions of echelon form, but we see the leading entry of the third row is 1, but it is not to the right of the leading entry in row 2. So, it is not in echelon form. Any matrix can be reduced to row echelon form by using a sequence of elementary row operations. Let us see what an augmented matrix is. Let us consider the following system of equations. X plus 2y plus 3z equal to 4, x minus y plus z equal to 6, and 2x minus 3y minus 4z equal to 1. We can write the system in matrix form Ax equal to B, where A is the coefficient matrix, X is the variable matrix, and B is the constant matrix. Its coefficient matrix is A equal to matrix containing elements 1, 2, 3, 1, minus 1, 1, and 2, minus 3, minus 4. Also, its constant matrix is B equal to matrix containing elements 4, 6, 1, using the coefficient matrix and the constant matrix, we can form a new matrix called the augmented matrix in the following form. The matrix contains elements 1, 2, 3 and 4 in the first row, 1, minus 1, 1 and 6 in the second row, 2, minus 3, minus 4 and 1 in the third row, which is a matrix of order 3 cross 4, and a vertical line is drawn to differentiate between the coefficient matrix and the constant matrix. Similarly, if we are given an augmented matrix, we can write the system of equations using that matrix. For example, if we have an augmented matrix containing elements 1, 4, minus 1, 2 in the first row, 0, 1, 2, 4 in the second row, 0, 0, 1, 3 in the third row. We can write the equivalent system of equations it will be x plus 4y minus z equal to 2, y plus 2z equal to 4 and z equal to 3. Now we shall discuss Gaussian elimination method. We can solve a given system of linear equations using Gaussian elimination method. The Gaussian elimination method involves the following steps. The first step is to write the augmented matrix of the given system of equations. The second step is to reduce the augmented matrix to row echelon form using elementary row operations. The next step is to rewrite the reduced augmented matrix into system of equations. And the last step is to solve the obtained system of equations using back substitution. Let us consider the following example. If we have the following system of equations, x plus y plus z equal to 6, 2x minus y plus z equal to 3, and x plus z equal to 4, to solve it by Gaussian elimination method, we have to first write its augmented matrix. That is, matrix containing elements 1, 1, 1 and 6 in the first row, 2, minus 1, 1 and 3 in the second row, 1, 0, 1 and 4 in the third row. Now we reduce it to row echelon form using elementary row operations. For this, we have to make all entries below the first non-zero entry in that column 0, and the leading entry should be 1. So we start with the first row. Here the leading entry is already 1. Now we have to make all entries below 1 in the first column 0. In the second row, we have 2 below 1. We have to make it 0. For this, we multiply the first row entries by 2 and subtract it from the entries of the second row. Also in the third row, we have 1 in column 1. We have to make it 0. For this, we subtract row 1 from row 3. And we obtain the following matrix: 1, 1, 1 and 6 in the first row, 0, minus 3, minus 1 and minus 9 in the second row, 0, minus 1, 0, minus 2 in the third row. Now we come to second row. Here leading entry is minus 3. So first we make it 1. For this we multiply row 2 by minus 1 by 3. We get the matrix containing elements 1, 1, 1 and 6 in the first row, 0, 1, 1 by 3 and 3 in the second row, 0, minus 1, 0 and minus 2 in the third row. Now we have to make entries below this leading entry in column 2, 0. For this, we add elements in row 2 with elements in row 3. And we get the matrix containing elements 1, 1, 1 and 6 in the first row, 0, 1, 1 by 3 and 3 in the second row, 0, 0, 1 by 3 and 1 in the third row. Now we come to row 3. Here the leading entry is 1 by 3. We have to make it 1. So we multiply row 3 by 3 and we get the matrix containing elements 1, 1, 1 and 6 in the first row, 0, 1, 1 by 3 and 3 in the second row, 0, 0, 1, 3 in the third row. Now we rewrite the reduced augmented matrix and equivalent system of equations. So we have the following system of equations. X plus y plus z equal to 6, y plus z by 3 equal to 3 and z equal to 3. Now we solve this reduced system using back substitution. We have z equal to 3. Put z equal to 3 in y plus z by 3 equal to 3. We get y plus 3 by 3 equal to 3, which implies y plus 1 is equal to 3, which implies y is equal to 3 minus 1, which is equal to 2. So we have y equal to 2. Now we put y equal to 2 and z equal to 3 in x plus y plus z equal to 6. This implies x plus 2 plus 3 is equal to 6, which implies x plus 5 is equal to 6, which implies x is equal to 6 minus 5, which is equal to 1. So we have x equal to 1. So the solution is x equal to 1, y equal to 2 and z equal to 3. We can further make calculations easy by making maximum entries in the echelon form 0 by using row operations. That is, if we make entries below and above the leading entries 1 of each row 0, then the calculations can become more easy. Now let us discuss inconsistent system of equations. A given system of equations is called inconsistent if it has no solution. We can find it from the echelon form of the augmented matrix. If all the entries in a row of an echelon form of augmented matrix except for the last entry are 0, then we have no solution. That is, if a row of coefficient matrix in the reduced augmented matrix that is, the reduced echelon form have all 0 entries and the entry in constant matrix is non-zero, then the given system of equations have no solution. For example, if reduced augmented matrix is given as the matrix containing elements 1, 0, 1 and 4 in the first row, 0, 1, 2 and 1 in the second row, and 0, 0, 0 and 3 in the last row. Here all the entries in the last row are 0 except the last entry, and if we write its equivalent system of equations, we get x plus 0 into y plus z equal to 4, 0 into x plus y plus 2z equal to 1, and 0 into x plus 0 into y plus 0 into z equal to 3, which is not possible. So it has no solution. Thus, in this session, we have learned how to solve a given system of equations using Gaussian elimination method. This completes our session. Hope you enjoyed this session.